what does that general addition rule include? Oh, we add, and then we subtract the intersection.
Wait, can you rearrange that to get your answer?
What?
Did you rearrange it? So it's
Yes.
probably A and B.
Yes. It's an equation, isn't it?
Yeah.
So remember, it's A plus B, but you see how I counted that twice? So we got to take that out. So, probability of A or B, what is that?
32.
32%, right? 0.32. And we'll say this is psychology and this is a foreign language. So what is the probability of psychology? So 0.17 plus the probability of a foreign language? 0.28 minus the probability of both.
Oh shoot.
So 0.32 equals 0.45 minus probability of A intersect B. And you can rewrite this, but I will also point out 0.45 minus what is 0.32? 0.13. Okay. So do not forget to pay attention to those details, right? The or instantly tells me, hey, I can use the union. And I know you say, okay, but there's an and. It's asking for the and. But we want to remember that A or B includes the intersection.
So that's
right?
All I do is I rearrange it to solve for A and B.
Right. And you can do that. Notice all I did was I just paid attention to the fact that I would subtract 0.13 to get the 0.32. So the intersection would be that 0.13. Sir?
Educated guess was right.
Let's make sure we know how to do it 100%
Well, no,
next time.
I know. Generally tell you that.
All right, number 13. Let's talk about this one. This one I intentionally picked earlier than one of the others because I realized that we need this background, this reminder, before we do some of the earlier questions I included here. So, how did we approach this one?
I made up some numbers.
Yeah, we don't want to do that, do we? Bryson, how'd you approach this one?
I most definitely guessed.
Most definitely guessed.
It's the answer, A by any chance.
Hey.
I did the tree thing.
Oh, what told you to do a tree here?
It's just like this percent has this, and then the percent of that having this. It's like a lot of information, so writing it down.
So a lot of information, but not only that, right? 90% of the people who have a particular disease will have a positive result. What should that remind us of? That's a conditional, isn't it? So it's 90% of those who have the disease will have a positive result. Right? So they either, what's the conditions? So they either have the disease or they don't have the disease. And based on whether they do or don't have the disease, they could test positive or... Now remember, we usually just write that positive or negative there, but what this positive really means is positive given they have the disease. Negative given they have the disease. They test positive given they don't have the disease, and negative given they don't have the disease. That's what's really happening there on those branches, right? Because it's coming after they do or don't have the disease. So, what's the first bit of information we really need to have? Well, what's going to go in these first branches? So how many have the disease? 5% of a certain population has the disease. So how many don't?
0.95.
There we go. How many are testing positive given they have the disease?
90% of that.
90% of them, right? So how many are testing negative given they don't have the disease?
They do have the disease.
Given they do have the disease. Thank you. How many are testing positive given, do we know how many are testing positive given they don't have the disease?
No, we don't need it.
Not yet.
I don't think we need it.
We don't need it.
You sure?
Yeah, I think the data is relevant.
I think it's important. How many test negative given they don't have the disease? 0.9. So this would be 0.1. Because what is the question asking? How many will test positive? This is testing positive.
Yeah.
this also is testing positive,
Oh.
right? So remember, you can test positive and not have the disease, so we need to make sure we do those full sets of branches. And so one thing I want to remind you, because I know I was talking about this with Deacon, and Deacon was like, I don't remember anything about the conditionals. We got to know the conditionals. What is the probability of A given B?
Probability of A intersect B.
So the intersection, so both happening, divided by the probability of B divided by the condition, right? Because we're not looking at everything, we're just looking at this condition. So how can I find out what the intersection is? How can I find just what this intersection is? Multiply by the probability of B. And so we want to remember this, right? So if I take the probability of the condition and multiply it by the conditional, I get the intersection. Here's my condition. Here's my conditional. And if I take 0.05 and multiply it by 0.9, I get 0.045. That is the probability of testing positive and having the disease. When I take my condition and multiply it by the conditional, I get the intersection.
So
you would need this as well.
No.
Oh no. So, what's 0.95 times 0.1? It's 0.095. So what percent of the population will test positive? What is it? 0.4, oh yeah, 0.14 or 14%. Notice this is why false positives and false negatives are problems, and why when we test, we have to check again, right? We don't just usually accept the results if we test positive, we usually would check again, because notice, is it more likely to test positive and have the disease, or test positive and not have the disease?
Test positive and have.
Look, I would say, look, test positive and not having the disease happens almost a full 10% of the time. Testing positive and actually having the disease only happens almost 5% of the time. Now, the likelihood of testing positive given you actually have the disease, much higher than testing positive given you don't have the disease. But the probability of testing positive actually happens more often overall when you don't have the disease. Yes?
So why is it 14%?
Because, okay, so the probability of testing positive is these two together, right? You can test positive this way, or you can test positive this way. You add those together, you get 0.14. Yep, good question. So, remember when we're given the condition probabilities, Deacon, we got 2 weeks left. Condition probabilities and those conditional probabilities, that tree diagram is a beautiful situation. Remember also, a very common thing that the test will ask is something like this. Hey, what is the probability of having the disease given you tested positive? In this case, do we actually have the conditional of testing positive? Say again, Josh?
I wasn't sure it was conditional looking at it.
It is though. So the reason we need to recognize it is because it says 90% of the people who have a disease will test positive. So there's the condition that they have the disease. So of those who have the disease, they are testing positive. So it is a relationship between those two. There's the condition that they have the disease.
90% of 5%?
So 90% of that 5%. You're right. That's why we got the 0.05045 here, Josh. That's why we got this. Because we multiplied, right? 90% of that 5%, they're testing positive and they have the disease.
Is that 0.045% of the entire population?
Well, that's the probability.
Okay.
So 4.5% of the entire population test positive and have the disease.
Alright.
Okay? What's your question, Josh?
Doesn't matter.
Josh, it does matter. If you want to ask the question later, let me know. I can't help you though if you don't ask the question. What I do want to point out though is notice lot of times what the test will do is they'll give you this conditional statement, which is the reverse of what we just had, right? But we can find it using this tree diagram because it's probability of having the disease and testing positive, which, do we already have that intersection?
Yes.
Yes? Is that 0.045? Divided by the probability of testing positive. Do we now have that? That's the 0.14 right here. Right? So don't forget that you can flip the conditional like that, and they do that pretty regularly on the multiple choice for the AP exam. Okay, test day. When are we taking this test? Monday, okay? Not this test, sorry. The inferences with means will be on Monday so that we can go over the demonstrated understanding for those who were not here yesterday. Mock exam, what time do you need to be here tomorrow? No.
7:30.
You need to be here before 8. I went by Chick-fil-A. I ordered chicken minis this morning. Again, if you want to just chip in a couple bucks just to help offset the cost, cool. If not, I'll eat the cost. It's fine. But I'll have chicken minis. I did a large tray of them. I'll be here about 7:30, 7:35. I'm picking them up at 7:20. I'll try to get there a little early. I will be outside at the teacher entrance right in the middle of the school. You know what I'm talking about?
Mhm.
Okay.
The one that goes into the English hallway.
Yes.
Okay.
So not the end, but the one in the middle that goes into the English hallway,
Okay.
right at the bottom of those stairs. So mock exam, 90 minutes to do multiple choice, 5 to 10 minute break, 90 minutes to do the free response. We'll talk about a couple things with that tomorrow. And yeah, so let's look at the demonstrated understanding. I do want to get to some more of the two variable data because even Austin was like, oh crap, there was bivariate data stuff in there. And so we want to get as much of that done as possible so that you have some of the background pieces. And unfortunately for you, Austin, literally one of the first things we're going to look at is one of the things you're like, dang it.
See, I guessed it, and I almost got it right.
Alright,
Maybe you just didn't work that.
so here's the demonstrator understanding that we did yesterday. For the most part, we did okay on these. I do want to point out a couple of things. The significance level of a test, just the significance level, is called what? Alpha. Just the significance level. Hey, guys. Just the significance level is alpha. But the observed, which is based on the observed statistic, is the p-value. Right? We've got to recognize that the observed significance level is the p-value. Hey, Peyton and Haley and Bryson, don't forget to print out my solutions so that you can also have those for any that we don't go over. Okay. So, I made a lot of notes for you.
I know.
I'll post it in the
I
Schoology,
know.
I guess. All right. So do not forget the power of a test is the probability of what? This is one of the ones that we have to remember.
Type 1 error.
No, alpha is the probability of a type 1 error.
Which question?
So alpha is the significance level and the probability of a type 1 error. What is power?
The probability of not having a type 2 error.
It's the inverse of a type 2 error, or the complement of a type 2 error.
Correctly rejecting the null hypothesis.
There we go.
Yep.
That's the language that they're going to want on the AP exam. Correctly rejecting the null hypothesis. It is the complement of beta, the probability of a type 2 error, but what it most accurately is the idea of correctly rejecting the null hypothesis.
You go over 2 because I'm so
Yeah. So, Aaliyah, you nailed this one. How does the sample size affect alpha?
It doesn't.
It does not.
We check.
At the very beginning of the test, you set what the alpha is, right? You set the alpha. The alpha is not affected by sample size. Not at all, right? Either alpha is 0.1 or alpha is 0.05. You set it, not determined by n. But as our sample size increases, what happens to beta? It decreases, right? If you increase your sample size, the likelihood of making that type 2 error goes down. And you didn't have to include this, but we want to remember, so what happens to the power?
Goes up.
So power increases. Okay. There are other ways to affect power, but one of the simplest ones is to increase the sample size.
Wait, why is it increased?
If you increase your sample size, the beta goes down,
Oh, yeah.
right? And remember, power is 1 minus beta.
I just remembered it as the power goes up, so I just need to inverse it.
Yeah, and you can remember, okay, sample size goes up, power goes up, so beta goes down. Okay. All right. For the most part, we were pretty good on this one. Just make sure that you actually run the test on these. Did anybody write down their p-value for number 6? Was it 0.044?
I have 0.0324. Wait, for number 6?
Yeah.
Yeah, 0.0324.
I
Or
messed it
325.
up severely, so no.
That's fine. Regardless, though, and I need you, Lexi, in particular, to pay attention to this because you've missed this a few times, and everyone needs to pay attention to this. The whole idea of the p-value is this is the probability of what?
Successfully, wait, you're successfully rejecting, no.
That's power. Probability of getting,
The value or more extreme?
so that statistic or more extreme by chance alone, assuming what?
The null hypothesis is true.
Assuming null hypothesis is true.
That's the first one.
Okay? So, what we're saying in this case is, assuming that the mean actually is 0, whatever x bar 1 minus x bar 2 is, the probability of getting that statistic or more extreme is what in this case?
0.0324.
So, Lexi, is that likely to happen by chance alone? I mean, how likely is that?
Not that likely.
Not likely.
No.
Remember, what is 0 shot of something happening? The probability is 0, right? What's the probability of it definitely happening? 1. So is that pretty close to 0? So that is so unlikely that we don't believe the null hypothesis, right? That is so unlikely that we reject the null hypothesis because there is convincing evidence for the alternative, right? That is such an unlikely p-value. That p-value is less than alpha. It's so unlikely to happen that I reject the null hypothesis because I have enough evidence for the alternative. Does that make sense? Notice though, that is why it is only C and not D. By the way, I do want you to notice which two should you have automatically eliminated? The first two. Why?
Those are trash.
Not because they're trash. Which one has a higher average? Side X. Should have never picked A or B, right? We knew side X had a higher average. We can see it there. And the likely, and then we had that less than 5% significance, or less than 5%, okay? Questions about that, number 6?
I don't know how my p-value gave me was so high, it was crazy.
Might just type something in wrong, so be careful typing it in.
I should have redone it because I was like, that's weird. But
Yeah. Number 7, do not forget, well actually in this case, do we have paired data or independent samples? How do we know it's paired?
Because they're gonna get twins.
And it literally says pairs of identical twins, right? And should I just look at the average birth weight of all firstborns versus secondborns, or should I pair the data together? Pair it together, right? I have a clear relationship between those two twins because there's inherent differences between each set of twins because of genetics from the parents, things like that. But if I can pair them together, I'm reducing, notice that language, because Logan, I think you had that on one of those things. Can we eliminate confounding? Nope, we can only reduce confounding. Can we eliminate bias? Nope, we can only reduce it, right? So we reduce the confounding, we reduce the bias. And so we're reducing the bias there, or the confounding there. Okay. I know the alpha level here was really low. Was it D on this one? We don't have time to go through this all the way, but D.
Wait.
Is that right?
It was
Yeah.
C.
It was C.
There you go.
No, A.
Oh, C. It was
Sorry.
bad. It was D. Yeah.
It was D, yeah. The p-value was 0.008. So,
Not
So-
like
So if
0.0014.
we're not given the, was it the alpha?
yeah.
Yeah, I
How
got
do we-
0.004 as well.
So
How
you
do we
run the,
understand?
well, you run the test,
Wait.
right? Because notice they're giving you, no, so significance level is alpha.
Yeah.
So when you ran this test, you get a p-value, at least looking at Deakins, of 0.08.
Yeah.
Well,
We got
Mine's
3.004
that's- oh, 0.0,
because it's not a 2.
I thought that was an 8 on
I
this.
have sloppy handwriting.
Yeah, so notice how that's less than
It was
0.01.
an 8 on mine.
So 1 to
Oh. It's less, but it's less than that, isn't it?
Yeah.
So you go to the lowest significance level possible. So
Okay.
notice it says you would reject at 0.1 but not at 0.05, but you would reject at 0.05. You would reject at 0.05 and also at 0.025. You would reject all the way down to here. Those are your alphas. Number 9 confuse you?
Yes.
So first things first, you got to be able to know what a type 1 error is. A lot of us identified a type 2. A type 1, that is when we, so we reject the null hypothesis when null is true.
The language of all these is just really.
Well, start with which ones we know that it would not be them. So,
D.
does he find convincing evidence?
Opposite. No way.
He does.
If he rejects the null hypothesis, did he find convincing evidence?
Yes.
Yes.
So
Okay.
D and E are out.
D and E are out.
So
Now, this is where you want to go back to the hypotheses. So, he's rejecting this null hypothesis. What does he believe?
Thought the alternate is true.
So that the true mean amount of homework done per night is greater than 1 hour. That's what he believes, but what is the truth?
they act. Well, they do.
That the true mean actually is 1,
Yeah.
right? So he rejected the null. He believes the alternative. He has enough evidence for the alternative, but the null is actually true. So A says he finds convincing evidence the students do homework for more than 1 hour per night, when really they're... So here's the thing. It's not about whether there is or is not convincing evidence. It's about the fact that the null is actually what? True. So which one says that he finds convincing evidence, but the null is actually true?
B.
Which one?
B.
B.
So why wouldn't it be A? 'Cause, I mean,
Because it's not about there isn't convincing evidence. There was convincing evidence, but the null is true.
alright.
There is convincing evidence, but the reality is at most they spend 1 hour.
That's fine. There's always two answers that it could be.
But this is why, and I need all of you to pay attention to this, that's why I would write this out to remind myself it's not about the evidence, it's about the truth in this case. That the null is actually true. Now, we usually don't know the truth, but that's why they ask what is a type 1 error, because we can define a type 1 error in this case. We don't know if we made it, but it's possible. So we talked about p-value again, right? The p-value is the probability of getting that extreme or more extreme. I think the most common answers were C and D, with which being incorrect. The most common answers I got were C or D, right? So assuming the null is true, and so notice that's why A and B are out, because what do we assume? We assume the null is true, right? But what is the probability of getting a mean of 1.09 if we're talking about a continuous distribution? That, hey, Bryce and Logan, I need y'all to pay attention to this one specifically. This is the most common mistake that people made on this one, because if you remember, the probability of getting a mean equal to this on a continuous distribution, that probability is 0. There is no area under the curve for exactly at that piece. It had to be at least, remember, that extreme or more extreme. that extreme or more extreme? P-value, that extreme or more extreme? Or if it's two-tailed, you have to look at both sides. We already addressed this one a little bit. What can affect power? Changing the what? Sample size. Is sample size up here? Actually, sample size is, but it says using a what? Smaller number of high school students. Would decreasing the sample size increase my power? No. What can also affect power, though? Alpha. Because remember, and this is what you want to think about, if you increase alpha, how does that affect beta? It decreases beta. So if you increase alpha, you increase the likelihood of a type 1 error, you lower the likelihood of a type 2 error, and if you lower beta, and power increases. Right? So if you lower alpha, then you're going to increase beta, and power decreases. Okay. So C.
I didn't even know that's what that was asking.
What do you think it was asking?
Like a more accurate order.
That's kind of true, but when it says powerful, you need to think power.
Okay.
Okay. Hey guys, you know with 12, the detail I want to point out on 12 is this. All inference procedures are built out of what? All inferences are built out of sampling distributions. And so when is the sampling distribution of X bar approximately normal? When is the sampling distribution of the sample mean approximately normal? So when the population is normal,
When the sample size is sufficiently large.
and so when we satisfy the central limit theorem, the sample size is sufficiently large. So why do we look at a graph of the sample data? Hopefully, if it's symmetric, we believe the population is approximately normal. Notice that word plausible, right? We can look at the sample and tell if the sample is approximately normal or symmetrical, but it's a symmetrical sample that allows us to think the population is approximately normal. All inference procedures, Haley, are built out of what? Sampling distributions. That's why we use X bar minus, and we use mu, but because the mean of X bar is mu. We technically use the standard deviation of sample means, but the standard deviation of the sample means is the standard deviation divided by the square root of n. It's all built out of sampling distributions. Yes, Bryson?
Can you explain plausible again? What still gives me?
It's just possible.
That's all it means.
Yeah, you say something's plausible, it's possible. So like, it's just, that's AP stats. So like when we say 0.03 to 0.12, right? 0.05 is a plausible proportion in that confidence interval. Do I know that the true proportion is this?
No.
But it's a plausible one because it's possible. That's all it means. Okay. Okay. Y'all made this one harder than it had to be.
What the heck is 13A? What the heck is 13A?
Yeah.
Hey guys, hey, hold up. If you want to run a hypothesis test, if you want to do a confidence interval, what you got to do?
I didn't know it was talking about this.
State later.
So the statistical procedures are state,
Those are the.
Plan.
Not the right thing, that's the steps to it.
hold up, those are the steps, those are the procedures. Those are the procedures. If you randomly assign or don't randomly assign, how does state, plan, do, conclude, change?
They don't.
They don't.
Oh
I
my.
said what?
If I get this one,
There might have been something, I think there was something else you added in that wasn't 100% accurate. I'll come with that.
I said like proceed with caution, but like
You can do them, it'll just be awful and useless.
Well, hold on, here's the thing.
Can I put your
We
finger
don't
grab?
trust the results, but do the procedures change?
I didn't say you can't generalize the population.
Hey, that's not the question though. Maybe I change it in the future and make it clear that it's randomly assigned versus randomly sample. But the whole point of this question is that the procedures do not change. Instead of getting upset about it, I'll take your test grade, I'll replace the demonstrating understanding grade. I still gotta do that with the last test, learn from it, grow and get better. So, I just need you to understand, it doesn't matter how you collect the data, the procedures do not change. Yes?
I thought you said independence doesn't apply in the experiment.
Correct.
So technically,
It doesn't have to be
the
independent
procedures
experiment.
possibly change.
No, state plan do conclude.
No,
Stay-
I'm saying,
it stays exactly the same.
like the conditions, like checking conditions.
Okay, conditions, one of the conditions might change, but the procedures as a whole do not change.
It doesn't have to be independent experiment.
No.
I know.
Because, well, what he's referring to is that 10% condition. You don't have to worry about 10% condition in an experiment because you're randomly assigning the entire sample.
Oh, yeah.
And so it's not about sampling from a population. It's not about bias.
So I still put it on the
trying to do.
Right. So how does the interpretation change? If we have random assignment, what can we establish?
Cause and effect.
There we go. That's the big thing I wanted to see. Random assignment, we can establish cause and effect. If there is none, no cause and effect. Right? Just, and hopefully, an inference about the population.
Oh, yeah. Is there a difference between inference and, well, I said correlation, but.
Correlation is between two variables. We don't always have two variables. That's a good question though. Alright,
Do we have time to work it out?
work what out? No, that's it. It's not asking you to do it. It's just saying if you are testing the hypothesis that means are equal for the population, how would the procedures differ, if at all, depending on whether you randomly assign or whether you merely observe? The procedures do not change. That's all. That's what I need you to recognize. And then here, how does your interpretation change? If you have random assignment, you establish cause and effect. If you don't have random assignment, no cause and effect. Right, Peyton?
I forgot my shoes.
Okay. All right. I need you to log on to a calculator. Yes, ma'am.
I didn't have to.
I logged on with it.
Try these two.
People crazy.
Upstairs. Here, upstairs.
No, I have to watch track meet. I'm leaving.
Oh crap, I wonder why.
What do you want to do?
It ain't got no gas.
What's up?
You need one too? Yeah.
I never understood baby back.
That's what I saw also.
Square it up on game. Square it up is what it's called.
But alpha and beta do have something to do with the same size. I guess, so you're saying alpha has nothing to do with. I got you. Remind me after class.
Is it this? Okay.
Hey Josh, dude, chill man, you got such a class right now.
What?
Everything's just chilling.
Okay, are we logged on? Everybody logged on? Ready to square it up?
Crap, I need to.
Grab one that has a hat on it. Alright, so really quickly, let's reestablish a couple of things from yesterday because this is the foundations for what we're about to do. Yesterday, we looked at this data for candy grabbed, right? And what did we call this type of graph right here? Scatter plot, right? We are graphing points based on individuals with two variables, and we said we were going to make a what from that scatter plot? A regression line, right? And remember, we ended the day talking about there's a best regression line called a LSRL, least squares regression line. Least squares regression line, LSRL. Pay attention to that because that's what this activity is supposed to help us understand. Okay, so go ahead and go to 1.2 for me.
They're doing hair.
Yeah, so you want to go ahead and have the squared up task. Go to page 1 of the squared up task.
Right up.
That's the one that's a TI Inspire file. Does everybody have the squared up task? We all good? Okay. So, what are we looking at in this task? What's up, Lexi?
Have you been in
Yes. I didn't put yours in because you hadn't finished it yet.
Do you need a
No, I took a picture or a scan of that one page. Alright, what do we have? So life expectancy for people or men and women. I think was it in the US? Does it clarify? Yeah. So move to page 1.2, life expectancy for men, women, and people in the US for every 10 years from 1900 to 2000. Yes, sir.
Is people the average? So the two?
Ish.
Oh, shit.
Ish. It's not just a pure average of the two, because if there's more women than there are men, the number of the women would more heavily affect the average, right? So it's a look at all people.
Okay.
Yeah. And more than likely, this isn't a true average because they probably didn't have data on every single person.
Full census.
So they probably did statistics, ran some stats to get this data. All right, so here's what I need us to do. What does it say after that? It says to go to page 1.3, create a scatter plot to illustrate the relationship between the year and the life expectancy for a person, selecting year on the horizontal axis, person on the y-axis. So
Would we do person on the? Yeah, I guess.
There's a real scattery plot.
Is it?
Right, I watched the video.
here's a question I have for you.
Pretty positive.
Okay.
Pretty strong.
Okay, so maybe how would we describe this maybe based on what we discussed yesterday? Maybe a strong, so we usually go positive, linear relationship. Okay? All that stuff together is called the what of the scatter plot? It starts with C. Correlation, right? Strong and positive, that's the correlation. Linear relationship. Now, what do we need to calculate to confirm that it's a strong, positive, linear relationship?
Do you need to analyze it?
We need to analyze it, we need to look at R. But before we do that, we're not going to do that right now. I need you to go to the, no, that's the last page.
You're the last page.
100%. You need the first page, this page. Okay, I'll look for it in a second. Okay, so I need you to move to the second page. Notice, actually you need to add the movable line, so follow the tech tip to add a movable line for me.
Wait, how do you do that?
Dude, read the page.
I can't read it.
Well, you're going to have a rough time on the AP exam.
I'm an illiterate teacher.
Here you go, Kate.
Add movable lines.
Gotta remind yourself.
Just movable lines. Who want what? What? Menu?
We got three lines.
Have we already added our movable line, guys?
Analyze?
Come on, add a movable line.
I see.
Yeah, movable line is right there.
Menu.
Oh, that's a
Oh,
real movable line.
Analyze.
it has the directions on that sheet of paper, guys.
Add a movable
Do I
line.
have to move it?
Well, you need to add a movable line. You will be moving it soon.
Oh, yeah, I did.
It's not gonna.
Good job.
Appreciate it.
Kenny, I think this one is a.
I probably need to click somewhere.
Okay. Do what?
Kenny, this one don't like people.
Well, she didn't add the scatter plot yet.
That's why.
You
The papers
know
have
that. Now add your movable line. All right. Everybody have a movable line. Their scatter plot ready to move to the next, to the back side of this page. Okay. Don't move it yet.
What's up with
Does it say to?
Yes, it says get to the last part of 3 minutes.
Oh, move the line near the middle of the line to change the y-intercept. Yeah, so
I'll put potential minus actual.
it just says to grab, I guess, do your best, I guess, right now, to move that line so that it approximates that data as well as possible. Do notice, if you move the cursor to the middle, and then you hold the center button down on the directional pad, that's how you translate it up and down. Notice what is changing about the equation. The which intercept?
X.
A Y.
The y-intercept. Y was mx plus b, right?
Yeah.
If I go towards the end, what's changing now?
Oh.
A little bit of everything, but it's also changing the what? Slope? Okay. So move your line around until you think you have a good regression line.
Why was there already?
I did this.
Okay?
I think
Undulating
about right
regression.
there, if you find.
Say again.
Undulating
I
regression.
think right there.
Good. What does it mean to regress?
I don't know.
What's
That'd
that?
Why is yours different?
What do you mean?
Not that.
Oh, I'm
Not
looking at it upside down.
This is-
See, this is how you know it's about regression. It's just terrible.
Menu,
I don't have shoes.
analyze,
I need to-
movable line. Yeah,
So
But I don't want to crease my new shoes, so I might as well just run barefoot.
there you go. All right,
Ah.
so,
They're really pretty.
say again, Bryson? Just whatever line you think would best approximate those data points.
we should have
That's a regression line. Oh, hold up.
$10 shoes.
Yeah, hold on. Don't do that.
Shoes.
That's way off.
I
All right,
just $10.
Like relation.
there you go.
I only had 8.
So, yeah,
30%.
so I'm gonna hit escape to get off that, and then you hit Control Z
That's a mobile.
to get back to where it's supposed to be. And then you move to the center to translate it up and down. Hit escape. By the way, guys, if you have it translated where you want it to be, hit escape and then rotate it separately. So it has that circular symbol there.
Like I did
Now I can rotate it,
that.
hit escape, maybe translate it again.
All
Alright,
Yeah.
I think it's a decision on it.
There are actual squares. Squares are
what's
like.
that?
Yeah.
And then this was.
It'll happen next
No, escape
month.
doesn't rotate
I
it,
might go back to
escape,
Bailey
you click
with
it,
control.
you
I need
hit,
to
so
know.
if you're holding on to it,
Because then
you
you'll
hit
maybe that
escape,
show you're
stop holding on
No.
to it,
See,
and then you move it
To be honest, I don't know if Miss Rhonda will take me back.
You got like all long distance, you got like the sprints too. I got the 8 shoes.
That's simple.
Not very
Hold it
artistic.
in, hit escape, and translate it again. You gotta play around with it, okay? Alright, so, let's look at, Peyton trying to kill me over here. Let's look at the back side. So, analyze the residuals. This is going ahead and getting us to jump ahead a little bit, but we need to talk about what a residual is, right, Austin?
Yes, we do.
Yes, we do. So, what does it say on the sheet a residual is?
Actual value minus predicted
value.
What does that mean, though?
It's the actual value minus the value.
What does that mean?
It's the value that is actually there versus predicted.
But what does that mean?
Like,
The correlation value?
basically it's the distance between like your line and the actual point.
There we go. That's what a residual is. The residual is how far is your data point from the line.
So it's just a standard deviation.
No. Because a standard deviation is a typical amount the data deviates from the mean. We will use the residuals. We will use the residuals to find the standard deviation soon. Yes, sir.
The closest line, or is it like vertical?
It's always vertical. Yep. Hey guys, hear it clearly on that. Because and we're going to talk about this in a second. Now I'm going to move my line to be a little bit closer. They said to look at which data point? 1950? Is that right? So, I think this is, so notice I can hover, Bryson. I can hover my hand over that data point, and I can find out which one is 1950. So what is the actual value for that 1950?
68.
For me, well, for everybody, it's 68.1, right? And then it says minus the what?
The predicted value.
How am I going to find a predicted value?
If you're to analyze it,
You're gonna use your line of regression.
Can you use my line of regression? You said do what?
analyze.
Analyze maybe
You plug in 1980, or what does that say?
1950? So
1950.
let me show you this really quickly. I meant to show you this yesterday. But this, I'm going to just approximate it to here. Okay. This is my regression equation right now. Okay. What's weird about this equation right now?
It looks weird.
Yeah, what in the world does that y hat mean?
Why?
Like P's at point estimate.
Maybe a y sample? Say it again.
Point estimate.
It's kind of like a point estimate. It's an estimate. Just like we did p hat was the sample proportion, right? In this case, whenever we say y hat, we mean a predicted y value. Because notice, this line right here, does it perfectly hit those points? So what is that line doing? It is predicting those points, okay? So whenever we say y hat, we just mean predicted. Now, a word of encouragement that I would wholeheartedly hold on to is, don't just use y hat and x. Because when we say y hat here, what do we really mean? What are we predicting? But what is the y value?
I don't know. That's what we're predicting.
Lifespan.
Aren't we predicting the lifespan?
Yeah.
Okay. What are we predicting the lifespan on? 0.28 times,
Various.
what is that x representing? The year minus 482.133. Remember, in statistics, nothing is a random number, okay? That's my y-intercept right here. Okay? So, we want to recognize, can you just do y hat and x?
We can,
You can, but does this tell you a little bit more clearly what's happening here?
a little bit.
A little bit. What am I predicting? The lifespan based on the year. Right? This is something where you can use either one. I love to use this form. There will be times on the AP exam where this form is actually more helpful. But Tyler pointed this out. How am I going to find my predicted lifespan then?
You use that equation on the board.
Yeah? How?
So whatever year you're going for, you multiply that by 0.28, and you subtract 482 from that number,
Where y'all getting this
and that gives you an expected lifespan.
So I want the predicted lifespan, right? What year am I looking at?
1950.
1950. So if I were you, I would do a scratch pad and I would type this out and let's find out what my predicted lifespan is.
The way they had it laid out on the exam, when they put the big negative number first, and then it went like.
I'm going to talk about that. I'll sweat it.
It's the same thing.
Okay.
Are y'all getting, are you getting those numbers?
By the way, everyone's going to have a slightly different answer here because you all have different regression lines.
Oh.
Yeah, I'm getting my regression line or my equation from what I have on the board. Everyone will have something a little bit different. Okay? So find out what your predicted value would be. So use yours though, right? Oh, so click on the line.
Wait, is it 0.28 or 0.21?
So write that equation out, put your year in there.
For the.
So yeah guys, use your regression.
That's the same
What do you
thing.
do? No, okay, so this is the scratch pad right here. Do you have your equation written out?
Oh, yeah, I guess.
Now remember, you have that equation, so try using that one, and then you hit this and go to the calculation page. You can also use that line if you want, just because you already have it written down, but.
Is this one on that sheet?
That's a great question.
Is it?
Is it?
No, I didn't see it.
It's 1950, right?
Yep, we're looking at 1950.
Mine's negative.
All right.
We're doing it for 1950. Sorry.
Yep.
What does the page say?
3.
I'm behind. Oh, oh, I didn't put a negative.
He has some. Back there. There was one.
So does everyone have their
Right with it.
predicted calculated?
You close.
In close?
Oh,
Is it allowed to be a negative?
is this supposed to be a very big number?
Oh, no, is it?
You put a negative instead of a minus. Hey guys, be careful that you put a minus instead of negatives. Because if you put a negative in there, right, the negative is next to the decimal, it's going to multiply instead of subtract. You should have somewhere around 63, 64, something like that.
Mine's 54.
That just means your line is way further away than mine
Wait,
is.
what is it?
Mine's
What is it
23.
supposed to be?
I got mine to be 63.867.
59.
But this is because you have a different line, right?
Mine's 20.
Notice your y, no.
Mine's at 23.
Yeah, because you have a way more negative y-intercept. Okay. It's fine, it's fine, you just have different Hey guys, remember, everyone has a different equation. You're gonna get some differences in there. Now, residual 68.1. So, well, that's my actual. And how do I calculate a residual? Actual minus predicted. And so in this case, my residual would just be whatever that is.
I got 13.2.
Oh my gosh,
Oh, yeah.
that's so far away.
44.5.
Oh, I have 13. Pretty proud of it. I was playing golf, that's pretty good.
What part residuals?
That's fine. My line doesn't look that far off there, so.
Okay.
Why am I copying that?
Um,
That's not the number that I had.
There's no way that's what your predicted should be. Because look, it's got to be above 60, doesn't it?
Are we still running today?
Do that prediction line right there.
I don't wanna run, no run.
Oh my gosh.
It's right there. T versus 1950.
I do have
He
a
just
line.
went to the 1950 doc. He's like,
Oh, I didn't.
542, my guy.
What I put in?
582. Hey guys, I want you to look at your lines again because I'm pretty sure no one's predicted for 1950 should be below 62 to 64. Just glancing at it, because if you look at the y axis, it should be 62 to 64. So check to make sure that you plugged everything in correctly. Yeah, that makes sense. So make sure you plugged it in correctly. It's not a super big deal, but we should all be somewhere around 62 to 64. What you did.
Oh, 62.
That's fine. That's close enough, right? Just look here, so like 1950, yeah, you're pretty close to 68. 66, 67 probably. Okay. Now, two things I need you to look at with these notes. If a data point is above the regression line, would the value of the residual be positive or negative?
What?
If a data point is above the regression line,
It would be positive.
what do we just get?
Positive.
We got positive, because when it's above, right,
Yeah.
it's a positive, which means our regression line underestimated. But because it's actual minus predicted, the actual is the data point. So if the data point is above, my residual is what? Again, if my data point is above, my residual is always going to be positive. Thank you. So what's going to happen if my data point is below?
Negative.
The residual is negative. Okay? Make sure you put that in the next two questions because that is important information. Okay?
I got another green one. Pretty proud of that.
No.
Okay. Now, I will say this, it doesn't happen a ton, but the AP exam does ask us to interpret residuals sometimes. Okay? So how would we interpret what that number means?
11.21 squares.
What?
Oh, wait.
My residual is 4.233.
Oh, my.
How would I interpret what that is?
My bad.
Your regression line is what, like, your prediction, I guess, underestimated the true parameter. No, I feel like parameters.
Say,
Underestimated the true value by 4.2 years.
and so, and that can work. I would usually start with the actual, right? The residual is actual minus predicted, right? So the actual, what? You said, you're talking about like the predicted, but what's the context? The actual what?
The actual lifespan?
The actual lifespan. In what year?
In 1950.
Right, so notice how in my context, both my explanatory and my response, the actual lifespan in 1950 is above or below my prediction?
Ooh, above.
It's above, because the residual was,
Four.
positive, which I think is what Haley was starting to say, but
Yeah.
why is it above? Because the residual was positive. Okay, there we go. The actual lifespan is 1950 is 4.233 years above the predicted. Actual minus predicted. So the actual lifespan in 1950 is 4.233 years above the predicted. You need to know how to interpret a residual. Yes, ma'am.
Okay, this is confusing me because mine's spitting out a negative.
But your predicted, is your predicted above? No.
So why is it years,
And
not percent?
No.
I moved the math though.
That's confusing on the freaking exam.
Where did you do your calculations?
You predicted already.
On 4.
I just
Girl, your slope is 0.343.
Oh, I thought you said we're doing the
really old stuff.
You used the right, so if you use my slope and y-intercept, that's what you would get. But you are using your slope and y-intercept. Oh. Alright. That will then work. Okay. So, I need you to pay attention to this. So, find a least squares regression line. A least squares regression line is found how?
By making,
Oh, we didn't actually show the residual squares yet, did we?
Nope.
Sorry. We need to follow the directions on the sheet. That's my bad. At the very top of this back page, it says from the menu options, choose what? Analyze. Then what? Before, oh, it is residuals, you're right. And then show residual squares, okay? So, notice how it actually drew squares. Where do you think those squares are coming from?
The distance from the actual point to
So,
estimated.
wait, what's the distance from the actual point to the line called? The residual. And sometimes the residual is positive and sometimes it is negative. And if I had the best line, you know what the sum of those positives and negatives would be? Zero. So how do we make sure it doesn't give me zero? What do? We created a...
Prediction.
Square.
Oh, wait, where'd the squares come from?
Square.
We created a square. Hey, because what's a positive squared? It's a... What's a positive squared? Positive. What's a negative squared? A positive, right? So we square our residuals. And what are we going to try to do with those squares?
Add them.
Well, it's already added. Sum of squares right here. What do you think we're going to do with those squares? We're going to make it the...
Average. I'm spitting.
Median.
The less, the least linear.
Wait, we want the what?
Least squares.
Oh, we want the least
Okay, I need to write that
squares. Because if we have the least squares, then our line is going to be the closest to all the data points. So, grab your line now, manipulate that line to create the least sum of squares.
Can you change the slope? Should there be an operation?
Yes.
Just make it the best line.
Maybe, but I want you to understand what a least squares regression line is first. So if you hit escape and you go to the either end, see how it has that rotating symbol? So now I rotate
I'll make your line
and then I translate.
pretty. That's probably why I had such a high thing.
And then I might rotate and translate.
I know you said we
Okay, it's on here. Hey guys, once you finish with it, right, answer numbers 5 through 8, we'll start talking about them soon. Analyze. Residuals.
Oh yeah, I got 80,000.
Remember? Analyze residuals, show residual squares. There you go.
I don't know how.
Find that least sum of squares.
Yeah, it was kind of fun.
Find out if you can beat my 47 that I currently have up there.
47 is cool.
I can't get underneath 100.
Have you rotated it all to change the slope?
How do you rotate?
No.
So remember, if you move the cursor to the edges, right, it'll allow you to rotate when you see that circular symbol. Okay, that's a little bit better, but we got all these big squares in there now. So maybe we translate some more.
You said what's your highest one?
I think I've gotten it down to like 41, 42. Right now I have 47.
Oh, I got 46 right now. Okay.
There you go, there you go. 46, 46. Oh. So there's how big those are. So remember, you can translate, but you can also rotate. So once we translate this up to make those squares bigger, maybe rotate it some more from the edge.
I got 41.
There you go. There you go. 41.4, 41.1.
You press it again to deselect that.
So do I have to do this on exists? Because I would be doing this.
No. I need you to understand what the least squares regression line is.
So,
So, has anybody figured out which set of data points most heavily are affecting the sum of squares?
2000s. What? 1960, 1970.
Middle.
I think.
go to the top.
It's actually these right here.
Yeah, I'm talking about those.
Right here.
Oh, wait, no.
Why are these most heavily, Austin, eyes up here?
Because there's so many of them.
Say it again.
Because there's so many.
So, if you don't have the line really close to these points, then those huge set of points, or that many points right there, are really going to change the sum of squares. Now, let's see if I can do it a little bit better. Ooh, there's 43.
Yeah, 57.
I got 41.3.
41.1.
Go towards the top of the line. You should get it.
I'm impressed because I don't know. I got 41.7.
God, I hate this
Okay.
calculator.
Okay. The priority though I want to ask is this. How do we determine the best regression line?
Can the calculator do it? Or do we have?
How did we know when we had the best regression line done?
Some
You wanna have the
closer
least
to
squares?
Okay. So the best regression line has the smallest
Yeah, 42, that's fine.
sum of squares. And where are those squares coming from?
The distance from the actual,
So what is that called?
the residual.
The residual squared, right? The sum of the squares, the individual squares are coming from the residual squared.
Where do I stand? I just start writing.
The 41.
Yeah, don't terribly sweat where you put it, just somewhere on that
At
section.
0. Not edge.
Now, I'm not gonna, because I'm gonna show you just how to use the calculator, Josh, in just a second, I know. But I do want you to notice something. In general, to have the smallest sum of squares, how many of your data points do you think need to be above the line and how many below?
What about an equal amount?
It needs to be half and half, right? So keep that in mind. To have that least the best sum of squares, it needs to be split in half roughly. Does that make sense? So we don't need to sweat all the other questions. That's the biggest thing. We need to make sure that we have that idea the best regression line has the smallest sum of squares. Now, anybody have a prediction about how I'm going to use that calculator to have the best regression line?
Analyze.
You're gonna use analyze.
So what are we going to hit before analyze?
Menu.
All right, let's go to menu.
And
Then
analyze.
analyze.
Then
You see anything from analyze?
Regression?
Regression. Anyone see anything there? So under, hey guys, y'all have already skipped over it if you don't know the answer. Show what? Show linear. Now pause and I want you to hear me on this. I heard someone ask, is this formula on the formula sheet? So put the calculators down, pay attention to this, get your formula sheet out. Formula sheet. Formula. Okay? I want you to look for maybe the equation of a line or something like that. Does anyone see anything for a linear regression line?
Y equals A plus BX.
Ah. Does it say just y?
Y hat.
Oh, it says what?
Y hat.
Where are you finding that?
Under descriptive statistics.
So look at number 1 under descriptive statistics.
Oh shoot.
Okay?
I had E was A plus.
Now,
I'll make this stuff in first.
I need y'all to pay attention to this. How different is that from mx plus b?
Not very.
If not,
Not very. But this is the more traditional statistics way to write it, which is a better way to write it. If you ever had me for algebra 1 or 2, you've probably seen me write it this way, because what is the y-intercept? That's where the function is, starts with an s. It's not really doing this, but it is a starting point, isn't it? And so it's where the function is kind of starting. And then we are repeatedly adding, and that repeated addition is known as the
slope.
Yeah. And so you can use either one, it does not matter. But the traditional one is that a plus bx. So notice the a, though, is my y-intercept. The b is my slope. Okay? Hold on to that. We're going to pick up on that later. But, so does it matter which linear you show?
No.
No, pick either one. I don't care. Pick either one. I'm going to go the traditional route and a plus bx. I like it better.
I like side square.
Is it okay if I went back through menu and then showed the sum squares again?
That's a great question. Would it be a good idea to show sum of squares again? Yeah, let's show that sum of squares again. So once you get your linear regression, by the way, do we all now have the same equation?
Yeah.
Does everyone have a y-intercept of negative 454 and a slope of 0.266?
No, sir. Oh,
Okay.
I got 41 now.
So what, yeah, so we're going to analyze residuals. And so the absolute best sum of squares is 41.0963. So you were super, super close. That was impressive. So, best regression line has the smallest sum of squares. And so, yeah, Josh, you don't have to do it by hand, but I want us to understand that that's how we get to that line is by the calculator finds the line that has the smallest sum of squares. Okay?
Is there a way to like take that equation out of there and like just put the x in, like straight from there, go after retype it?
What do you mean?
Like let's say you're finding y hat, you gotta take like the guy simply like kind of like copy and paste that equation. Right?
No. Maybe.
Just
I'll have to think about it.
What?
I'll have to look into it. Alright, hey, guys, we gotta keep going. We got 13 minutes.
Are we still running stairs today? Kinda late.
No, we ain't gonna have time at this point. It'll have to be on Monday after the test. Alright, hey, so let's look at the second page of this task. Notice what we have now done is analyze regression. We showed linear, we showed our residual squares, and so you can answer these questions, right? The biggest thing though, I want us to look at 12 and 13, right? Because otherwise you're just reporting values. That's not cool. We need to look at the cool statistical stuff. So what does number 12 say?
What advice would you give a friend? No, I'm not reading. Never mind.
What would we tell someone?
Yeah, just get the least amount of squares.
There we go. Find the least sum of squares. And what's going to be the best way to find that least sum of squares?
Do the show the thing.
Yeah, right? So, is it number 12? Is that what we're looking at?
Yep.
Right? So, we want the least sum of squares. And by the way, where are those squares coming from again? Hey guys, where are those squares coming from?
Residuals.
There we go, from the residuals, right? Least sum of squares, and the calculator can do that. You remember also yesterday when we did that in the list and spreadsheets page? It'll do it in the list and spreadsheets as well. And so we'll do that some more in a second. Okay. Now, we have got to talk about number 13. 13 is something that shows up on every AP exam, whether it be multiple choice or free response. It will show up on the AP exam. So, I'm going to show you something that I wish I had been shown. Because once I realized this, it made things so much easier. So what does it ask us to do? in number 13?
Interpret the slope and y-axis.
So slope and
y-intercept.
y-intercept, okay. Notice I rewrote this again with my variables in there for context. So before you can interpret, you got to start with the what?
Context.
You need the context, yes, but there's something I want even before I even focus on the context. If I want to interpret the y-intercept, what do I need?
The y-intercept.
I need the y-intercept, right? What is my y-intercept?
400 something.
Negative 454.364.
Is that my entire y-intercept, or is there something else?
No, it's the
Plus.
whole equation, isn't it?
No, that's the.
No.
No. What do you know about every y-intercept that's ever existed?
It's 0,
Oh,
Oh, the x value is what?
0.
yeah.
Do not forget, guys, a y-intercept is a point. Where this point, this 0, is it x or is it y?
X.
It's x, so it's 0 what?
Y.
0 what? Look at the equation. 0, what is my x?
Years.
Years.
So this is my year. What's this negative 454.36?
I mean, it's a lifespan.
It is a lifespan. There's another word I'm looking for though. There we go. It's a predicted lifespan.
Who's living negative?
Same. Who is living negative 454 years?
That's just
Nobody.
equation for it, never mind.
That's just the equation for it. This is the issue. Hear me on this. This is the issue with something called extrapolation. When you extrapolate, you go beyond what the data is for. This data is for 1900 to 2010. So can I go to the year 0 AD?
Probably.
No,
Oh.
right? The US did not exist in the year 0 AD.
Or did it?
It did not.
Our freedoms always have been.
So, but this is also why it's not the lifespan, it's the what? What's this hat?
Estimate.
That's the
predicted.
predicted. So how would I interpret this? In,
That's a pretty terrible predicted lifespan.
I'm aware, but this is how we would interpret it. In what?
In year 0 AD.
In the year 0 AD.
This is so good.
Alright, let's see, 0 AD.
Can I say it
In
on
your 0 AD, you've already been dead.
The predicted.
So in the year 0 AD, the what?
Year 3014.
Say it again, Ashton.
The predicted lifespan is negative 454.364 years.
Can I just write that equation?
Okay. I know that's a terrible prediction. This is why typically we would actually rewrite the data so that the year 1900 was the year 0, right? And then the year 1910 is the year 10. The year 19, and then that would change the y-intercept. The slope would stay the same, but the y-intercept changes. But it also doesn't matter. The point of this is, how do we interpret? In this beginning, the predicted, and hear me clearly on this, if you do not use the word predicted, you are going to miss out on credit on the AP exam. Because it is not the lifespan of Americans. That does not exist in the year 0 AD.
Oh, yeah.
The predicted lifespan is negative 454.36 years. Okay. What do we still need to interpret?
In time, well. Oh, the,
Slope.
The slope. Now, this is the part where I really wish someone had shown me this. So, my slope is what?
0.266129.
How in the world am I going to interpret that slope?
in a way.
In a way. Well, first off, how do we calculate slope?
Oh, is it like every year the lifespan rises by 0.2661 years?
Very close. There's one detail I'm going to push on. But also, how did you get there?
The slopes rise over which.
There we go. Say it again. And I need you to pay attention. The slope is what? Rise divided by run. Now, at the same time, Austin,
Sorry.
what's another way to say rise divided by run?
Slope. Changing y over changing x.
Say that again. Change in.
Y over changing x.
Okay. Rise.
What? Why is there
That's the Greek letter delta. The Greek letter delta means change. Hey, no, he did not. In math and in science, the Greek letter delta just means change.
So for every year, the predicted lifespan of Americans.
Thank you. What was the key word you were missing?
Americans.
Nope. Nope, there's a P word. Predicted. Because in this, it is not the change in Y, it's the change in the predicted lifespan. Divided by the change in the year, right? So the change in the predicted Y, the change in the X, right? And notice this 0.2661 would be understood to be divided by 1. When you interpret slope on the AP exam, you have to use predicted, because is it about the actual data points you're discussing or about the predicted line? The predicted line, right? The regression. So, every year, and one thing they do like to see is every extra year or every increase in 1 year. Notice how I'm using that number. So every increase in this.
Is this the second sentence?
This is the interpreting the slope.
Okay.
Yep. So every increase in 1 year, the predicted lifespan increases by 0.2661 years. Okay. So every increase in 1 year, the predicted lifespan increases by 0.2661 years. Every increase in 1 year, the predicted lifespan increases by that many years. Notice by labeling, right, it makes the interpretation way easier. If you try to do it without the labeling, some of us will be okay. But I promise you, by labeling your X and your Y with the year and the predicted lifespan, labeling your slope with the change in year and the change in lifespan, change in Y hat, change in X, is going to make the interpretation easier. I struggled with interpreting slope and y-intercept when I took AP Stats. Once I saw that, though, it made a whole lot more sense. Label, 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 label. What are we going to do, Bryson, for that interpretation? We're going to label. Now, I don't really have time for that right now. I know, right? Okay. We'll do more with that second page later, but
We have 2 minutes.
I know. I did put this in here.
When are we supposed to run up the stairs?
We didn't have time today. So I will say this, we don't have time right now. We're going to complete page 4. Actually, yeah, let's do this. Add some pages really quickly. Get the least squares regression lines for women and men. Write your equations, the sum of squares. Actually, just do the sum of squares for the regression equation. Don't do your own. So, if you look at the back page here, right, I need you to do a regression equation in the calculator for women and for men, and do the sum of squares, okay? Just get those equations so you can do numbers 1 through 4 for homework over the weekend. So you would change your y-axis to men, there you go, and it should change that equation slightly. So yeah, you don't actually have to create a whole new graph page, you can actually just change the y variable to men versus women, right?
And would this graph still stay on here even if we take the hat off still?
Yes, it will. So if you want to take this calculator with you and leave the other calculator, you can do that as well. But you need your equation, your sum of squares.
The one we added, or like the one that I predicted?
Say that again.
Is this sum of squares on here the one that I predicted, or the actual?
You want the one for the
Are you
regression.
understanding?
How do you know which one?
I'll show you in a second. So, hey guys, finish up any progress checks. Do note, I sent y'all some AP free response questions to help you prepare for the test on Monday. If you want to do those, I sent the solutions as well. Mock exam, you need to be here before 8. Again, I'll be here, try to be here at 7:30. So if you make sure that
So actually, just, that's very clearly the movable
I'll be
line.
driving.
Delete it. And then click
Oh,
on
it's in Porto.
You okay? And that's the actual.
So,
0.0005 seconds.
do not take a calculator unless you,